Hi, this is Ms. Trevino, and I'm going over the 2020 Physics Midterm Study Guide. So here we have Unit 1, Linear Motion. That's objects moving in one direction. For number 1, we're going to fill in the following table using the following terms. They're broken down into scalars and vectors. Remember, scalar is just a number. It's the magnitude of something. And a vector is a number with direction. So it's the magnitude of something with direction. So any one of these that has direction is going to be a vector. Everything else will just be a scalar. So acceleration does care about direction. It can be positive or negative, so that's a vector. Distance does not care about direction. That's a scalar. Displacement, it cares about your final position and your initial position, so it does care about direction. So it's a vector. Speed is only positive because it does not care about direction. Velocity can be positive or negative, and that's because it cares about direction. Remember, if it's going left or down, it's negative. If it's going right or up, it's positive. Force is the same way. It's the same thing as velocity with the up and down, left and right. So force is a vector. It cares about direction. And finally, momentum does as well. Remember, momentum's a vector. There are positives and negatives. Number 2, if a bus travels 780 kilometers in 6.5 hours, calculate the speed. Then convert to meters per second. And then I let you know that 1 kilometers equals 1,000 meters and 1 hour equals 360 seconds. So the formula for speed is distance over time. Our distance is 780 kilometers. And our time is 6.5 hours. So that's going to be 780 divided by 6.5. That's going to be 120 kilometers per hour. But then we want to convert it to meters per second. So we're going to need to convert 780 kilometers to meters. We're going to do that by multiplying it by 1,000 since there is 1,000 meters. So that's going to equal 780,000. 780,000 meters. And then our seconds, we have 6.5 hours. And each hour is worth 3,600 seconds. So we're going to multiply 6.5 times 3,600. We're going to get 234,000, 23,400. That's our seconds. So now we're just going to divide our meters by our seconds. 780,000 divided by 234,000. Our speed in meters per second is 33.33 meters per second. So we calculated the speed for kilometers per hour, and we calculated the speed for meters per second. All right, number 3. A runner starts and finishes a 3-kilometer run at the same point. What is the runner's displacement? So the key here is to look at displacement. It cares about which direction you're going to, which direction you're going to go. So if he starts and finishes at the same point, here's my runner. He's running. But he's going to start and finish at the exact same point. So the displacement is 0. No displacement. Because he's starting and finishing at the same point. Remember, displacement cares about direction, so it's your final distance minus your initial distance. If your final and initial are the exact same number, the exact same point, you're not going to have any displacement at all. All right, number 4. Acceleration is defined as the change in velocity. Remember, the formula for velocity, for acceleration is your final velocity minus your initial over your time. So the final minus initial, that's a change in velocity. Number 5, a hiker walked 9.18 kilometers west and 2.81 kilometers north. What is the magnitude of the hiker's displacement? Hint, draw the vector arrows. So we're looking for displacement, which cares about direction. We know that the hiker walked 9.18 kilometers west. So let's draw what that looks like. He started here. He went 9.18 kilometers west and 2.81 kilometers north. So we're going north, 2.81 kilometers. So we want to know the displacement. We want to know the initial and the final. That's what we care about. We don't care about anything else. We just care about the final position and the initial position. So if you draw this correctly, it is a right triangle, which means you're going to have to use the Pythagorean theorem to figure out the actual displacement. So a squared plus b squared equals c squared. You have to do 9.18 squared plus 2.81 squared equals c squared. So on my calculator, 9.18 squared plus 2.81 squared. Oh, let's make sure we use parentheses just in case something goes wrong. 9.81 squared, parentheses, plus 2.81 squared, close parentheses, 92.1685 equals c squared. To get rid of a squared, you have to do the square root. So the square root of 92.1685 is 9.6. So that means our displacement is 9.6 kilometers northwest. Remember, we're displacement, we care about direction, so we're going to have to add the direction. This is just displacement. If this question was asking about distance, distance doesn't care about which direction you're going in. It doesn't care about your final minus your initial. Distance, you just add them all up. So for distance, we would do 9.18 plus 2.81. And our distance would be 11.99. Now, it wasn't asking for that, but I just wanted to show you the difference between displacement and distance. All right, let's go on to number 6. A car starts from rest, and after 10 seconds, it is moving at 22 meters per second. What is the car's average acceleration? So on this problem, we're looking for acceleration. That is our A. And we are given our time, which is 10 seconds, and our velocity, which is 22 seconds. Now, it also says that the car starts from rest. That's going to be very important. Remember, acceleration is a change in velocity. It's our final minus our initial divided by our time. We need final and we need initial to solve for acceleration. Well, it starts from rest. So initially, how fast is it going? 0, since it started from rest. That means 22 meters per second is our final velocity. So when we plug in our equation, we're going to do 22 minus 0 divided by 10 seconds. 22 minus 0 is still 22 divided by 10. Our acceleration is 2.2. And our units are going to be meters per second squared. All right, let's go with our next one. A car accelerates 6 meters per second squared. Assuming the car starts from rest, how much time does it need to accelerate to a speed of 40 meters per second? Well, we're looking for time for this problem. We know the car accelerates at 6 meters per second squared. So that is our A. The car starts from rest. So again, our initial velocity is going to be 0. How much time does it need to accelerate to a speed of 40 meters per second? So if it starts from rest and accelerates to 40, that's our final velocity. Remember our formula for acceleration? It's final velocity minus initial velocity over our time. So when we're plugging in our numbers, we know acceleration is 6 meters per second squared. We know our final velocity is 40. And we know our initial velocity is 0. Then we're going to divide that by our time, which is what we are looking for. So we are going to have to do some algebra on this problem since our unknown isn't what it's equal to. Since time is a denominator, we're going to need to multiply it to both sides to get it to the top. This cancels out over here. So we are left with time multiplied by 6 equals 40 minus 0, which is just 40. Now all you have to do is divide both sides by 6. 40 divided by 6 is 6.666667. So, oh, and that cancels out over here. So our time is going to be 6.67 seconds. And I just rounded it. I don't need to add all those numbers. All right. In the next set of questions, we have Abby Cadabby moving along a number line. Using the steps below, graph Abby's motion. Abby starts walking at x equals -2. So imagine this is 0. If x is -2, that'd be 1. We could call this one -2. Then she moves to the right to x equals 2. So this would be 1. This could be +2. Then moves to x equals -1. This is -1. Then finishes at x equals 3. So that's 2. This would be 3. So let's graph what that looks like. Abby starts at -2, then moves to the right at x equals +2. Then Abby moves to x equals -1. Then Abby finishes at x equals -3. So this is where Abby started. This is where Abby finished. What is the distance? Now remember, distance does not care about direction. It just cares about the total distance traveled. So at first, from -2 to +2, let's count how many places that is. That's 1, 2, 3, 4. Then they go from 2 to -1. So let's count that. That's 1, 2, 3. So that's 3 places. Then we go from -1 to 3. So let's count that. That's 1, 2, 3, 4. So when we add up all of the distances together, 4 plus 3 plus 4, total distance is 11 places. Displacement, again, displacement is your final minus initial. It doesn't care about your total. It just cares about final minus initial. So final was 3. Initial was -2. 3 minus -2, that changes it to 3 plus 2, which gives us 5. Again, that's the difference between distance and displacement. Distance cares about your total distance traveled. You're adding everything up. Displacement only cares about your final position minus where you started, your initial position. All right, let's go to number 10. In a position time graph, what does the slope represent? Well, remember, slope is y over x. That's what slope is. So if we're doing our y, which is position, over our x, which is time, position divided by time, if we look at our formula charts, position divided by time, that's velocity. Or it could be speed. And that's for a position time graph. The next question asks, in a velocity time graph, what does the slope represent? Again, slope is y over x. Your y is velocity. Your t is time. If you look at your formula chart, v over t is this one, velocity over time, so that's your acceleration. So the slope for a position time graph is velocity, or speed. The slope for a velocity time graph is going to be acceleration. Number 12, according to the graph below, what was the bicycle's acceleration between 0 and 5 seconds? So this is our graph. Our velocity between 0 and 5 seconds. That's what we care about. We're looking for acceleration. And acceleration is your final velocity minus your initial velocity over your time. So if we go from 0 to 5 seconds, that's going to be our time. At 5 seconds, we have a velocity of about 10. At 0 seconds, we have a velocity of about 0. So when we plug in our numbers, our final velocity was 10. Our initial velocity was 0. Our total time from 0 to 5, that's 5 seconds. So we have 10 minus 0 over 5, which 10 minus 0 is still just 10. That 0 does nothing. So 10 divided by 5. Our acceleration is 2, and the units for acceleration are meters per second squared. All right, let's go to number 13. Number 13, we're drawing some graphs. This is for a position time graph. If you're doing this online, all you have to do is double click them and it'll take you to a drawing where you can just add arrows yourself. But since I'm doing it on paper, I'm going to write it in. I want an object accelerating, and this is a position time graph. Position or distance, they're the same thing. So if I'm accelerating, that means I'm going faster and faster each time. That means my distance is increasing greatly as time goes on. So if I'm accelerating, I'm going to have a curve. Accelerating will give me a curve. If I'm moving at constant speed, again, this could be position or distance. I'll use distance. If I'm moving at constant speed, that means my distance isn't changing drastically, but it's increasing at a constant rate. So it's going to be a straight line with a slope. It's going to be straight with a slope. And if I'm at rest, that means I'm not going anywhere. My distance isn't changing. My distance is going to stay the same. So if this was a position or distance, this time I'll use position, that means I'm not going anywhere. So I'm going to have a flat horizontal line. No slope at all because my distance isn't changing. It's not going up, it's not going down. All right, 14. Draw a velocity versus time graph. Again, if you're doing this online, just double click it and you can make your own arrows. But now I want velocity and time for an object that's accelerating. If you are accelerating, that means you're speeding up. You're going faster and faster. That means your velocity is going to increase. It's going to change. So if your velocity is changing, you should have an upward slope or downward. It could be either direction. You could have negative acceleration. So it's going to be straight with a slope. If I'm moving at a constant speed, that means my velocity is not changing. It's going to stay the same. If my velocity is not changing, I need a flat, straight, horizontal line because it's not changing. It's constant. And if I'm at rest, that means I'm not moving at all. That means I don't have a velocity. My velocity would have to be 0. So at 0, that's where my velocity needs to stay. Because I'm at rest, I don't have a speed, I don't have a velocity. And the last set of questions for Unit 1, I do believe this is the last. Yes, the last set of questions for Unit 1 is talking about this graph. So this is distance and time. Let's go ahead and label that. Distance, time, or lowercase d, sorry. Which time period has the greatest velocity? How can you tell? Just by looking at this graph, you can answer that question. You don't need to solve anything. The greatest velocity is going to be from 0 to 2 seconds. How can you tell? Because it has the greatest slope. It's steeper. Anytime you have a steeper slope, that means you're increasing it more than if you had a slope that was not as steep. So, greatest velocity, 0 to 2 seconds. How can you tell? Because it has a steeper slope. Number 16, what is the total distance traveled? So distance doesn't care about direction. All we care about is your total distance traveled. So we're going to have to add all the distances together. From 0 to 2, we traveled a distance from 0 to 6, so this is 6 meters. From 2 to 4, we went from 6 to 6. We didn't travel anywhere. We stayed in place, so that's 0 meters. From 4 to 7, we went from 6 meters to 9 meters. So that's 7, 8, 9. That's 3 meters we traveled. And then finally, we went from 9 to 5. So we went 1, 2, 3, 4 meters. Remember, distance doesn't care about direction, so we're just going to add these all together. 6 plus 0 plus 3 plus 4. 6 plus 0 plus 3 plus 4. That gives us 13. So our total distance traveled was 13 meters. The next question asks, what is the displacement of the object at the end of the path? Remember, displacement is your final minus initial. Our final was at 5 meters. Our initial was at 0. So 5 minus 0, our total displacement is just 5 meters. Which segment is the velocity equal to 0? So if your velocity is equal to 0, that means you are not moving. If you're not moving, your distance isn't changing. The only time we have distance not changing is this time period right here, from 2 to 4 seconds. And again, we know that's not moving because the distance didn't change. The distance stayed the same, so we know we are not moving. Number 19, what is the velocity from 4 to 7 seconds? So on this one, we want the velocity from 4 to 7 seconds. So from 4 to 7 seconds, this is what we're doing. Velocity is going to be distance over time. Our distance traveled over our time interval. Our distance traveled, we already calculated that was 3. Our time, if we're going from 4 to 7, that's 1 second, 2 seconds, 3 seconds. So we have 3 meters over 3 seconds. Our velocity would have to be 1 meters per second. That's how fast we're going from 4 to 7 seconds. That means we're increasing by 1 each second, which makes sense on the graph. We're going up 1 each second. And the last question for Unit 1, what is the displacement from 2 to 4 seconds? So we want displacement. That's our final minus our initial. From 2 to 4 seconds, so that's 2 to 4. So we only care about this part right here. Since it's final minus initial again, our final position was at 6. Our initial position at 2 was still at 6. So that means our displacement is 0 meters. We didn't go anywhere. From 2 to 4 seconds, we didn't go anywhere. Our displacement is 0. So that's all I wanted to talk to you about for this first unit. I'll make another video for Unit 2.